So I am especially delighted to introduce the next speaker because she's my granddaughter. Well, actually, she's my academic granddaughter. So Alyssa Pierson will talk to us about designing semi-cooperative robots to improve team autonomy. Alyssa did her PhD at BU, advised by Max Schwager, and then she did a postdoc at MIT in my research group. Alyssa works on group robotics, multi-robot systems, and her work has been recognized in many ways, including with the Rising Star Award from Mass Robotics and the NSF Career Award. So let's give Alyssa a very warm welcome. I'm so excited for your talk.
Well, thank you, Daniela, for those kind words. And thank you, everyone, for coming to this keynote session. I know there was the robot parade going on, so I appreciate coming here and listening to our parade of multiple robots. So today, I'd like to talk a little bit about my work in designing semi-cooperative robots to improve team autonomy. So if we think about our cities now, and we think about our cities in the near future, the hope and the goal why we're here at these conferences is that in the future, we'll have robots everywhere. And these robots will take on all sorts of different types and forms, from drones to legged robots, autonomous vehicles, autonomous buses, delivery robots along our sidewalks. And these robots will be everywhere in our cities and hopefully work alongside us and fulfill all sorts of different tasks. And so this wasn't meant to be like an I Spy of robots here, but really that we can take these robots and we can integrate them into our city. And these robots of the future, they're going to be distributed, diverse, and dynamic, which introduces all sorts of interesting research questions and what I like to call semi-cooperative robots. So suddenly when we have all of these robots all in the city, we've gone and we've designed them in our labs and we've written all of these wonderful policies and algorithms for them to work alone, but now we're throwing them all together out in the world, and we have to figure out how do they get along. They're not adversaries, this isn't competitive robotics, but at the same time, they're not centrally coordinated, and we still need them to operate and have emergent cooperation with one another. So what are some examples of what I call semi-cooperative robots? These are things like heterogeneous teams. How do you take jobs designed for one robot and transfer them to different form factors and different types of robots in the world? How can these robots interact with unknown agents? So for example, if your monitoring robot encounters a pizza delivery robot, how does it still ensure that that pizza is delivered on time? Because nobody really wants a lukewarm pizza to be delivered. And also, when we talk about unknown agents, they could also be human agents within the world, and human agents that take on maybe different form factors that we typically see in our training data or in our lab settings. And finally, how do we resolve when these agents have conflicting goals? So for instance, autonomous navigation, where they both need to negotiate different intersections. All of this poses the question that we as researchers need to solve this cooperation puzzle. We've got all of these highly capable individual systems, and we need to bring them together and fit together nicely so that they're still as capable as a group out in the world as they were individually in our labs. So I propose that by studying these interactions, it allows us to create safer and more robust autonomous systems. Now, of course, there's many, many people in the field studying different types of interactions, studying different types of cooperation and coordination in multi-robot systems. And I could fill an entire hour just listing papers. But in this short amount of time, I wanted to distill this down into what I think of as some of the three main approaches to modeling behavior in these systems. So we have one way to model behavior, and one way to model this cooperation is through what I call geometric style policies. These are the safety nets of our system. They're very fast to compute, and often they bound the actions that something could take, human or robot, to a specific region. So these are things like your classic reciprocal velocity obstacles, control barrier functions, reachability sets, Voronoi cells, etc. Moving up in complexity, we also have interactive models of cooperation and behavior. These often take a game theoretic design where we have more complex behavior that emerges, and we often predict these actions from optimization. And finally, of course, we have our learned policies, where if we're given sufficient data of a behavior, we can really capture those nuances and emergent behaviors for specific domains. And so the question is looking forward, is there any one policy or any one thing that can solve all of our problems, solve all of our cooperation? And that's why I'd love to tell you about the life-changing magic of Voronoi cells. No, I'm joking. This isn't the only solution, but this is one I've looked at quite extensively. So if you're interested in Voronoi cells, I would love to talk to you about how amazingly flexible and coordinated they are at many different things, both from task allocation, coverage control, and even things like pursuer evader games. However, one limitation of Voronoi cells is it assumes that everyone is playing by the same rules, everyone's got the same control policies, and more or less has the same function or capability in the world. More recently, what we've started to look at in our group is looking at different questions that move beyond these assumptions of everybody's the same or everyone's cooperating equally. So some work we presented yesterday is looking at how new types of decompositions in an environment can improve coordination in heterogeneous teams. So we imagine that you've got this team of robots, and maybe they're tasked with serving different monitoring of targets throughout the environment. And maybe you've got one really capable mapping robot, and it has amazing localization, and it can build this perfect map of the world. But its teammates are much simpler and have lesser compute, lesser reasoning capabilities about the world. So can we use things like geometric decompositions of the world to abstract down the highly complex world that the nice robot can make, so that way our teammates can coordinate and still accomplish these goals as a team? Another question we like to ask or look at is when we talk about information in planning and information in predicting out what agents are going to use, what information is important when we're trying to plan these policies? So there's a lot of promising work in belief-based planning, in dynamic games, and in the field of stochastic dynamic games. Of course, in these, we have to balance off this idea that we can propagate all of these predictions, propagate all this uncertainty forward, with the reality that this isn't very scalable in either the number of agents or the planning horizon that we could take. And so some active work in our lab is asking the question of, well, what information is important? Can we only propagate some of that belief space? What are these key pieces that we need to really model this behavior while still getting the same emergent behavior as if you were able to propagate the full belief space? And obviously there's a spectrum. There's some point in the middle where we can only propagate a little bit of information and it looks great. But if we propagate nothing, then our agents don't behave as we want them to. And this question of why we might care to find simpler and simpler policies really is when we talk about scaling up to operating in large crowds. So this was work from a couple of years ago where we wanted to ask the question, for an autonomous wheelchair navigating in a really cluttered environment, this hallway in CSAIL, in the status center, what is like the minimum amount of information we could give this robot to still have a pretty good navigation? And this is a simple 2D LiDAR sensor. It's not doing prediction of the pedestrians. It's not trying to figure out exactly what everyone's going to do. And instead, we're getting this relatively smooth autonomous navigation through this corridor and still maintaining a nice pathway through. And this is important because as we think about sending robots out into unknown worlds, we want to think about what those minimum safety nets are that still ensure safe operation and interaction with a lot of unknown things without requiring lots and lots of models, lots and lots of predictions. Building on that, more recently we've looked at also with this navigation. In the previous example, we had the wheelchair fully autonomous, where it was really shuttling the passenger from point A to point B. But now we're imagining we have the user wanting to give a little bit more input about the direction that they're going. And so that asks the question, how do we handle disagreement between our autonomous systems and our users of that system? And so when we think about humans driving autonomous micromobility, such as autonomous wheelchairs, but also possibly teleoperating these vehicles, oftentimes we use haptic interfaces to give a little bit of feedback to the user about what the robot sees. That, of course, introduces a lot of questions about how do you take the rich information available to a robot and distill it down to something like a single channel of haptic feedback. And so, in particular, what this work wanted to look at is when we have an autonomous agent that thinks it knows the way to go, but doesn't know about the dogs in the scene. So it knows about the cones, it doesn't know about the dogs. How does it correctly interpret the human's intention to take a new path and work together in a way that we have this co-navigation between the human and the autonomous system? And so the final thing I want to talk about is how do we really bring in different preferences and different decision-making policies under a framework. And this was really motivated by the social dilemma, which is where we have this autonomous vehicle that needs to make a left turn across traffic, and there's this human driver. And as we've driven in traffic before, and as we know, there's this decision we have to make as drivers. Do we go before? Is the other driver going to yield for us? Or do we wait to make the left turn until it's safe? This is a social dilemma, a case where the situations in which the collective interests are at odds with the private interests. Now, this is something that's studied quite extensively in social psychology. So I know it's Thursday afternoon, I know we're a little sleepy, but we're going to go ahead and do some audience participation here. All right, so the classic example is that we go into a room and you're sat down and you say, okay, here's $100, you need to split it with a stranger. Now, show of hands, who gives the $100 to the stranger? Anyone? Okay, well, that would be called an altruistic behavior. That means the other person entirely gets this reward and you don't keep any of the reward, the $100. And we're going to represent that as this angular notation where we've totally increased the reward to other and no reward to ourselves. All right, show of hands. Who says, let's split it 50-50? All right, so that is a pro-social behavior. We've split the reward exactly half and half. And finally, there were a lot of hands down before. Who says, it's a stranger, I don't know them, here's $100 for me? All right, yeah, some sheepish hands with that one, right? So that is what's known as an egoistic or a selfish behavior. All the reward stays with you. And what we saw here in this audience is actually pretty common for a lot of social systems. So from large studies, we see that typically 40% of people are this pro-social 50-50, 40% of people are egoistic, and there's a small sliver of the population that is altruistic. I'll just comment that I've done this talk at museums with children, and most children would like to do 50-50, and many more children will give $100 to a stranger. So maybe we should take some inspiration from the children here and share a little bit more. But anyway, so we thought this is a really nice model. This weighting of rewards is a really nice way to compare how we might resolve these dilemmas. And so maybe we could use these principles, the social value orientation, to resolve these conflicts in autonomous driving and other planning problems. And we're going to create joint reward functions that include altruistic, pro-social, and egoistic behavior. And we'll even find some competitive behavior, which in the analogy of our $100 is like you keeping the $100 and then stealing $5 from the stranger as well. And so we say that it's those altruistic drivers that yield and those egoistic drivers that you have to wait for. And it turns out allowing these variations do help improve predictions, and so sometimes it's embedding the variations in the models themselves. And so in closing, my pitch is that by studying these interactions allow us to create safer and more robust systems. And so thank you all for your time, and thank you for letting me run a little bit over.
Thank you, Alyssa. So we only have time for a quick question. Is there a quick question from the audience? You know, we do have this competition going between the left side and the right side. Is anybody going to? Okay, go ahead.
Yeah, so I think the question was, we see at supermarket parking lots, people don't return their carts even though they're maybe supposed to?
That is the
Yeah, so I would probably argue that we probably need to incentivize cart return more, give a reward, and in fact, Aldi does this. You get 25 cents back if you return your cart, and they don't clear as many carts as other supermarkets. So maybe it's incentives.
Okay, to be continued, because incentivizing people is a very, very interesting and challenging question. So thank you very much, Alyssa.